let me remind you what we said last time. Vorticity itself can be understood as a local angular velocity. So there are a lot of forces in the fluid, and generally speaking, you can form a torque, and it generates rotation. Anyway, we introduced since rotation is always associated with antisymmetric tensor, the natural object to introduce the angular velocity is we used, of course, to define the angular velocity as a vector, which is fine in three-dimensional space, but it's just because in three-dimensional space antisymmetric tensor is equivalent. It has the same number of components and transformed in the same way as a vector. It's just for the same reason we used to think of a magnetic field as a vector, but in fact it is hidden antisymmetric tensor. Actually, there is a lot of similarities and analogies which we will be exploiting between vorticity and magnetic field. By the way, what would be the analog of velocity in the case of magnetic field? Suppose you switch to electrodynamics. And then why I'm saying that there is a similarity between vorticity introduced in this way and the magnetic field, which formula for the magnetic field resembles very much this one. Yeah?
Curl of A.
Curl
of the A field.
Yes. It is expressed in terms of vector potential, and just as there you have you can write down the identity on omega, which guarantees that it's presentable in this way. Plus we already seen these things. By the way, again, in the case of magnetic field, what is this equation? What is the meaning of this? How it looks and what it means?
Divergence of the magnetic field.
Right. And what it physically means? This indeed transforms to divergence very easily. But what does it mean, that the divergence of a certain field? Well, for example, what does it mean in the case of electric field? Divergence of the electric field is not zero, it's what?
Rho over F.
It's density, or if you have point-like charge, then the flux lines actually emerge or go into this electric charge, and basically this relation means that magnetic flux lines that there are no in Maxwell's theory there are no magnetic charges. So the one more preliminary mathematical, or it's not even mathematics, I would say notational comment, is how things are related. I mentioned that this is equivalent to a vector in 3 dimensions. So in 3D, you have a very important object, and in 2D the object which we have is here is the tensor epsilon alpha beta gamma. Here is epsilon alpha beta. In general, the number of indices is the same as dimension of space, and they are defined in this way. They are numerical. When you have a 1, 2, 3, the trivial permutation, they are equal to 1, and all other components are obtained from this by -1 to the parity, to the number of transpositions you need to make to come to this. Epsilon alpha beta is even simpler. It's epsilon 1, 2 is 1, epsilon 2, 1 is -1, and all other things are 0. What is remarkable is that we have two types of numerical tensors. We have delta alpha beta and epsilon alpha, the Kronecker tensor and antisymmetric tensor. And both of them are important. Actually, very important. Mathematicians usually love to write epsilon and delta proving rigorous theorems, but these epsilon deltas are much more important than theirs. To be fair, I guess it was mathematicians who invented this anyway. Now, what is remarkable is that you form scale. You have in 2 dimensions. You have if you multiply it two vectors by delta alpha beta, you form a scalar product which is invariant under rotation. But you also can form a scalar product. It's in fact, we will use this notation for it. But what I'm telling you is just something useful, but not very deep. But it's just, as I said, it's just notations. Moreover, you have 2 types of scalars under rotation. They, however, are different. So this one is A1 B1 plus A2 B2, and this one A1 B2 minus A2 B1. And here, of course, you will have a vector product. These bracketed product will be vectors. Here they are scalars. There is, however, when I'm saying, by the way, I hope it should be clear, but I will mention it briefly anyway, that when I'm saying they are scalars, what do I mean by that? I mean that if I substitute instead of A1 cosine theta plus A2 sine theta, and so on, then the thing will not change. The primed products will be the same as unprimed. One more comment, which again will be useful, is that we can write it down in complex notations. If we can introduce the complex coordinates and actually epsilon tensor, delta tensor is analogous to 1, to the unity. What is the analog of epsilon tensor in complex notations? Or I shall ask you how these 2 products look in complex notations. Let's start with the first one. If I have 2 complex, I can replace vectors by complex numbers, and then it will be replaced by what? It is pretty simple. Under rotation, under this rotation, how A and B are transformed, to answer this question. So if you rotate like that and then add these quantities, what is A? A prime will be what? So you will write down corresponding formula for A2 prime and so on, but you can figure it out. Yes, please. Yeah, it's just the multiplication by A and correspondingly B prime. This is rotation in complex coordinates. And now we have to form two scalar products, two quantities which are invariant under rotation. How we do this? When you have A and B, what will be the simplest combination? It's simple. It's easy question. What will be the simplest combination which is invariant under rotation?
A star B.
Yes, and if you force your intellect, you also find a second combination, which is AB star. Okay, and but now how these guys are related to these two combinations? We have two invariant combinations here and two invariant combinations here. They are not literally the same, but how they are related? Well, you see, here we have this thing symmetric under A and B. So you expect and you get, or it is a real part of AB. This guy is we have to divide it by I in order to make it real. So this is imaginary part of AB. And more generally, epsilon tensor is always just multiplication by I, is equivalent when you go to the complex notation is multiplication by I. What else will we need? We will need all this. That's why it's all elementary stuff, but useful. We also can visualize epsilon multiplication by epsilon tensor as a rotation. Which kind of rotation? So if you have A prime alpha, this is a rotation of the vector A. And it's a 90 degree. Notice if you perform it twice, you get 180 degrees, which is simply reflection. So multiplicating it twice gives you -1, and that's the definition of I. I mean imaginary units, not a person. All right. And notice that things in 2 dimensions are very cute. we will see how they allow us to solve the problems of the flow past airfoil, for example. It's quite wonderful, complex analysis, quite wonderful, and naturally people tried to generalize this construction to 3 dimensions, where you have epsilon, alpha, beta, gamma. By the way, what kind of object it describes? These multiples. Here you have 3 vectors to multiply. And what is it? First of all, what is you are certainly familiar with this combination. And secondly, the second part of the question is what it geometrically means. While here we had, you can also ask the question of what it means geometrically in terms of 2 vectors.
Still happens a triple product.
How you call it?
Triple product.
Triple product, exactly. And what it means here, it's the area of this parallelogram, and this is 3-dimensional volume corresponding to this. And now one more, I'm taking too much time for it probably. But there is one more important and interesting thing. So these both guys are scalars. They are invariant under rotation. However, they are different type of scalars. There is certain difference between them. Not under rotation. But what can you say? Which symmetry, under which symmetry these guys behave differently? Yes.
Weaver symmetry.
The what?
Weaver symmetry.
Yes. How you see this?
You get a negative sign in the second equation.
Yeah, that's right. If you reflect, say B, you see that B1, for example, you reflect B1 by using mirrors, and then this changes sign. You change B1 and A1. This changes sign. This doesn't. So it's called the standard term here is pseudoscalar. So this guy is a pseudoscalar. This guy is a scalar. But when we are not interested in reflection symmetry, then we can call them both scalars. All right. So we derived last time the equation for vorticity. And this equation in 2 dimensions, as we say, vorticity must be always like that, simply because it's antisymmetric, and therefore there is only one independent component here, and so you can write it like that. You notice that this relation is invariant under rotations because of what I said. You multiply it by, say, 2 vectors, and you will get scalar equal to scalar. But since epsilon tensor is present, vorticity is a pseudoscalar. Not that it will be well, it will be somewhat important to us. Just as magnetic field in 2 dimensions. In 2 dimensions, magnetic field, if the blackboard is 2-dimensional manifold, magnetic field must be perpendicular to this, and that when you do reflections, it changes sign like epsilon. Okay. And what was most important is that from the equation, from the Euler equation, I looked at, incompressible fluid. The pressure is defined from d alpha is equal to 0. And as we said many times, if we differentiate it, take divergence, and so on, then we get pressure explicitly in terms of the velocity. For incompressible fluid, it's okay. And what is very important is that when you cross-differentiate to obtain the equation for vorticity, you cross-differentiate and you get the equation omega alpha beta plus some stuff which is proportional, which I will write down a little later. But on the right-hand side, you will get 0 because you have d alpha d beta minus d beta d alpha. In particular, in 2 dimensions, in 2D, omega dot plus d lambda omega is equal to 0. And that actually tells you that quite important thing, that if perfect fluid in the infinite volume it can be irrotational. The vorticity could be 0 everywhere. And moreover, if it is 0 at the initial moment, then it will stay 0 according to this equation. Because omega 0 is a solution of this equation, unlike the equation V equals 0, because we have pressure, you cannot really say the same thing. All right, and then we looked at the meaning of this equation. Before we go to real vortices, we have to analyze this equation is very generic and very interesting. I will go to higher dimensions a little later, but we now have to study the solutions. We shall again make a mathematical digression, which is the following. Let's suppose that we have some velocity which depend on y and t. And we look at the linear partial differential equation. So we have a function f of y and t satisfying the equation it looks like the equation I just talked about. But what is the real well, but nevertheless I decided to introduce a new letter, which means there is something different. So what is, apart from the difference in letters, what is the difference between this equation and this equation? The meaning. As written, they are identical. But nevertheless, their meaning is somewhat different. What is f here and omega here?
Vorticity or any function?
Yeah, well, yeah, that's really the point. The point is that here vorticity is not an independent function. It is defined by this equation is highly nonlinear because you have to substitute omega expressed in terms of the velocity back here. Nevertheless, and it turns out to be extremely useful to first analyze a simpler problem where f is simply an independent function. It's not a function of velocity, not expressed. So the first, and I must say, I will show you how to treat such equations. And it's a very useful skill because such equations appear very, very often, and you have to, and you have to get used to them and to the method of characteristics, as it is called, which I will briefly explain to you now. Well, first of all, let's look at the simple example. Let's solve simple example, and then we will generalize it. Let's suppose that we have let's even take it constant first. Let's solve this very simple equation. First of all, the general solution of this equation, well, the solution is fixed. You have to fix first the initial data. So we fix the initial value of the function f, and then as I said it already many times, that by Taylor expansion in time you can generate first derivative. First derivative is explicitly expressed, second derivative, and so on. So you do expect that the solution will be fixed if you fix the initial data. Now, what it tells us is that when you shift things by delta y, that things shift simultaneously when you shift t and y. In fact, I will probably simply write down the solution. In this case, it's very easy to find just by trial and error or by change of variables. You always can change variable so that the equation becomes df dxi new variable is equal to 0. I will simply write down the solution. And the solution is and let's check that this is a solution and discuss its meaning, and then after we understand the meaning we will solve this equation. Actually, the statement which we will arrive at will be that you can reduce solving this partial differential equation to solving ordinary differential equation. And in many cases, this ordinary differential equation is solvable, like it is here. And so let's check that it's indeed the solution. That's simple. df dt is f0 prime of y minus vt. df dy is minus excuse me, you have to multiply it by minus v when you finish. df dy is just f0 prime of y minus vt. When you multiply it by v and add, you see that the equation is solved. Now, what does that mean? Imagine that initially f is some quantity concentrated in a small domain in y. So let's imagine that it's localized some lump for a given y. What the solution tells you? How to?
Squares that travels together.
That what?
The lump moves out of one lump.
Yes. Yes, it tells you that the lump moves along the specific trajectory, and what it tells you is basically that if we have y here, t here, at time 0, if we have been here at time 0, we draw the lines y equal to vt, and plus x. And so if we want to find the value of f here, we just have to backtrack. This line, this trajectory, it has several names. It has the name of Lagrangian trajectory of this fluid particle, as we started with. It has the name of characteristic. It may have some other names in different physical circumstances, like light rays and so on. But what is important is that suppose we are interested in the value of f at this space-time point. This is the space-time point. We have to backtrack in time to the time 0, and the value of function f here is simply inherited from this value. You see? So the value here is just if we had some initial distribution of f's, they are simply translated here. And this is the backtracking. And now I'll give you a general answer. So basically you can say that f goes with the flow. It's not, there's actually a class of physically very interesting problems when you have a turbulent flow and you put some objects in it and you see how the object moves in the turbulent flow. So in this case, when the object does not back react on the flow, does not change the flow, it's called passive scalar. So there is a passive scalar. And it's actually, people right now are quite, well, for a few years, recent years, were very much interested in how to describe the passive scalar in a turbulent background. I shall notice that there's also, we will, running somewhat ahead of myself, that we will treat also passive vectors and passive tensors, which are, but I'm not ready to explain this yet. Passive scalar means that it just goes with the flow, as here. Now let's do the analogous thing here. Let's look. Let's suppose that we have this relation, and let's consider a differential equation. In general, the equation is called the equation for characteristics. Namely, it's very simple. This is precisely the equation which at the beginning of this course we wrote down for the Lagrangian trajectories. But this is differential equation which you are supposed to solve with the initial condition that it's not, sometimes it's not, you can choose different initial condition. Anyway, what is quite remarkable is that now we will show the same thing happens as here. What can you say? This is the characteristic. This was the special case of this equation. What can you say about the value of function f as you move along the characteristics. This function f characteristic here was this. What happens now? Let's take the solution and see how it changes along the characteristics.
It's constant.
It's constant, exactly. Now this is the general statement, and that's the way you solve this partial differential equation. You find characteristics, and you see that the function is constant on characteristics. Let's check it. It's all very elementary. It's both elementary and confusing, because when you start, well, you will see there's some subtlety in applying this method. So let's suppose we have a differential equation, and let's suppose that we have the function f, which solves the passive scalar, which solves this equation. Let's see what happens then you are on the characteristics. On the characteristics, where y is a solution of this equation. Now, let's take the time derivative. We have df dt plus y alpha dot df d alpha dy alpha so the characteristics, the function is also constant on the characteristics, but the characteristic is different. Generally you have to solve this equation, and sometimes it's possible, sometimes it's not. But in all cases, but it's of course always much easier to solve the ordinary differential equation than the partial differential equation. The huge progress here is that we reduced the solution to this problem, and the solution is this. You first find the characteristic, which is something like that, and then you say that you find the characteristic which passed through the given point at t equals 0 and at the time of observation. And then you simply say that the solution will be constant on these characteristics, and that's it. You can also show somewhat more explicitly. Maybe you can figure it out. Well, it follows immediately from this picture. So on each characteristics f, another name, by the way, for characteristics is a streamline in the fluid. The function is constant, so you can ask me, okay, but what is how to find the answer? What is the explicit form of the answer? And the explicit form, suppose that I solve this equation, and I find explicitly this solution, which is actually quite simple, as you see. Maybe quite. If, for example, in this case, the equation is simply y dot is equal to v. V is a constant, so we have y equal to x plus vt, and that's the equation for characteristics. Generally, it's some complicated function of x and t, but let's suppose we find it. What is, and suppose you know f0, the initial value f0 of x. So tell me what to do with this. How can I write, how can I immediately write down the explicit answer? If I know this, I more or less know the answer. Well, you see, that's, if you have difficulties, that's why I said it's elementary, but slightly tricky. You see that it takes certain mental effort to backtrack things on along the characteristics and write it down as a formula. It's intuitively easy to understand what it means to be constant on a characteristics, but in any case, without further ado, the answer is, when you see the answer, it will be obvious to you. The answer is this. It's f0 of x of y and t. So you have to invert this function. That's backtracking. Inversion of this function is backtracking. You find x as a function of y and t, and you plug it into the initial data, and that's the answer. See how it works here? X, we invert this function, which means x is y minus y vt, and here we get this answer. Okay, so again, as I said, when you have vector and tensor fields, you can solve analogously the problem of, as explicit as here, you can solve the problem for passive tensor of passive vector. All right, so we have the solution. The whole discussion was in order to understand that vorticity moves with the flow. Vorticity satisfies this equation. And this relation means that along the characteristic it remains constant. By the way, one more definition of characteristics is the following. It is when you perturb the system at the initial moment, there is a signal, and characteristic is the trajectory of this signal. What I mean by that is that if you have the initial function, you perturb the initial function, say somewhere here, and then perturbation will be propagated along the characteristics. Now let's find some simplest solution of this equation, of the flow with the vortex. It is actually, you can always set omega x to be, let's take it to be kappa multiplied by the delta of x. So let's imagine that we have vorticity concentrated at a certain point. We have to check whether it's consistent with the equation and what it really means. If we manage to do this, then we can combine different point-like, it's a point-like vortex. Let's find the distribution of the velocity corresponding to this. thing. We have to solve the equation epsilon alpha beta d alpha v beta is equal to kappa delta of x. Now we can look for the solution. It's actually convenient to look for the solution in the form I should explain. Generally, we have two components of velocity. So it should be two arbitrary functions. Here is one arbitrary function, which is called the stream function. Why it is one? What have another possibility, more general possibility for two functions would be d alpha phi plus epsilon alpha beta d beta phi, d beta psi. In this way, we express velocity in terms of two things, two arbitrary functions. Nevertheless, in the case under consideration, we can set phi to 0. Why is that? Which physical assumption we used by setting phi to 0?
Does it have to do with us only caring about the curl of V for the vortices?
Actually, remember I said we assume that the fluid is incompressible. Incompressible means that divergence of V is 0. That's the continuity equation. When if you set density to incompressible means the density doesn't change, and you have general continuity equation. That's general, but if you assume that the fluid is incompressible, which is very often very good approximation, you simply set rho to 1 or some constant, and then you get the divergence as 0. Now, if you take the divergence of this guy, it's 0 because epsilon is antisymmetric. But this guy, the divergence is not 0. So, and indeed, you see, let's crudely count the number of functions. V alpha has two components. There are two arbitrary functions, and they are both presented here. But this is one functional relation. So if you solve this condition, there will be only one arbitrary function, and this is the stream function. So in the incompressible fluid, we will have only stream function. This function is also needed, or it's called the potential. So this is potential stream function. Suppose that the stream function is 0 for one moment, and the potential is not. What kind of physical situation, which kind of physical assumption it will describe? So if no potential, we say that this equation is identically satisfied. Okay, and now suppose that we have maybe I shall write down this relation. How omega is related to the stream function. Let's relate omega to the stream function.
Is the curl of the streamline?
Well, curl for how you take curl of scalar. It's a bit difficult.
So I mean, we know the relation between V and
Yes.
omega.
Yes.
So we just apply.
Yes,
beta.
you are absolutely right. And if you apply it as you could have expected because of symmetry, it's simply the Laplacian of this function psi. You see, when you differentiate the There is a useful algebra which you use, useful tricks with epsilon tensors like that. If you have epsilon alpha beta, epsilon gamma delta, you can always write it down as in terms of Kronecker symbols. I shall do this in a moment, but first you tell me why it is guaranteed that this combination is expressible through deltas. I shall write down the answer, but you can meanwhile figure out the answer is delta alpha gamma delta beta delta. And you use this with algebra, but what I wanted, in passing, I wanted to stress why it is not surprising that this...
It's symmetric under reflection.
Exactly, yes. Under reflection, epsilon changes sign. So epsilon cannot be expressed in terms of delta, but the pair of epsilon can. Actually, and that refers to any dimensions. If you multiply epsilon tensors even number of time, it's delta. Okay, so we find a very simple solution. We have to solve this equation. And this is electrostatics, practically. You have the, if you actually consider psi as a potential, then this is electric charge, and that's the point-like charge. That's the Poisson equation. And in 3 dimensions, this equation, what would be the solution? What kind of solution would have in 3 dimensions? That's something very familiar to you, just...
1 over r squared.
1 over r for psi. For potential is 1 over r, electric field is 1 over r squared. Okay, now in 2 dimensions, it's actually quite... Let me notice that how could you foresee this 1 over r solution? It's just scaling. In 3D, it's psi divided by r squared. And the delta function behaves like r to the minus 3. Because, is it clear why the delta function scales like...
Because the volume integral has to go to constant.
Yes, exactly. Exactly. And so you get psi 1 over r. In 2D, we have something puzzling. But this cannot be right because if you take a constant, you will get 0. You will not solve the equation. So what really happens?
Is it ln?
Yeah, the logarithm. Actually, if you take, for instance, dimension to be, well, let's take it 2 plus epsilon, you will get r minus 2 psi, r minus 2 minus epsilon. Psi will be proportional to r minus epsilon. And if you calculate the coefficient, you will find that the coefficient is inverse with epsilon. So this is a logarithm of r as epsilon goes to 0. So, and we find the psi function, it's actually kappa divided by 4 pi, I guess, logarithm of r squared. And the velocity, you will see how I get 4 pi, you will see. You can, of course, get it hundreds of ways. The velocity is kappa divided by 2 pi, epsilon alpha beta, x beta divided by x squared. And that's the distribution of the velocity for a single vortex. And that's the building block from which we will start really building an interesting solution to the interesting hydrodynamic problems. So let's draw the picture. What are the lines, streamlines of the velocity? If you try to draw this, notice that at each point the velocity is orthogonal to the radius vector. So what would be the line of if streamline is the line such that at each tangent at each point is the velocity. That's the streamline. So how to build, how to view the streamline for this single vortex?
Concentric circles.
Exactly. You see, when we take a radius vector, it is always perpendicular to this thing, and this 2 pi you can is just the fact that the circulation, if you integrate it around the velocity, you get the circulation, and it is equal to kappa without any. It's of course a matter of definition of kappa. You could absorb 2 pi inside kappa, but that's more convenient. All right. All this is fine, but now let's start something non-trivial. It's clear that vorticity, which is sitting here, it is not velocity here. It's not moving. It's consistent to have the vortex, the single vortex, sitting at the particular point. But now let's consider 2 vortices. So let's look at the situation when omega is and here the problem will be that it's in principle, it should satisfy this equation. And this equation will not be satisfied if x1 and x2 are just constant, because in this case, if all these are constants, omega dot will be 0, while this product will not be 0. So it will be inconsistent to think about vortices located at some 2 points and sitting there without moving. In fact, we must, it's not a matter of choice, but we simply must consider the solution of the following form. the vortices must move. And how to find these trajectories is we will find it through this equation. And the beauty of it is that we will, in a moment, we will obtain the system of equation which treats not the from this hydrodynamic equation, it will follow that there are equations for this part, for these points, location of the vortices. As we said, V alpha is we can actually probably simplify the notation. Let's consider, it's equally easy to consider the arbitrary number of vortices. And V alpha is 1 over 2 pi sum over kappa A x minus x A epsilon alpha beta x minus x A beta So this is a superposition of vortices, and we must figure out how to define their motion. It's actually quite simple. When you take omega dot, you get sum of A kappa A d alpha delta of x minus xa multiplied by xa alpha dot. I simply differentiated this thing in time. And now you have to compare it with V alpha d alpha omega. And then equate the coefficients between the delta at the delta functions. And I will write down the answer, and it will be obvious to you immediately that what this answer means. So again, the technique is just, the rigorous technique would be to multiply this thing, multiply by derivative of omega, and compare the coefficients at the derivatives of the delta function. But the answer is so simple that it's better to start from it or to guess it from the very beginning. The answer is the following. Xa alpha dot is equal to epsilon alpha beta so we have this, that follows from this cancellation of the delta prime terms. But now if you look at it, you probably can put it in simple human words, not in formulas. What does that mean, this equation? This is what is called Kirchhoff equation. And it's very important and beautiful. It has beautiful features. But first of all, its meaning is strikingly simple. No. Look at these formulas, and what is this quantity? Suppose we have only one extra vortex. So suppose A is equal 1, B is equal 2. Huh?
It's the velocity of one component.
It's what?
The velocity of one component.
Yeah, it's a velocity of, so this is the velocity induced by the vortex B at the position of the vortex A. You see? So what it simply tells you is something very, very nice. You have all these different vortices with different vorticities and so on. Each of which creates its own velocity field. And each given vortex it creates its own velocity field, but it moves in the velocity field created by all other vortices. So it's kind of a model of human society that you have this self-consistent motion of all these objects, and in order to find the motion, so you can write it down as simply d alpha of xa, where v alpha of xa is the velocity, v alpha of x, its velocity created by all other vortices. So now this equation is actually extremely interesting, and people still working on it in relation to turbulence, etc. There are many interesting features here. First of all, well, let's solve some most simple problems without the equation, and then we will go back to the equation. So let's suppose you have two vortices which are, suppose it rotates counterclockwise, and the second one with the same also rotates counterclockwise. The other situation is this one. When you have two equal strength vortices, but in this case they both are rotated in the same direction, here in the opposite direction. And the question is how this thing moves using this physical insight. So the general approach would be write down this equation and solve it. And it will be, you will be asked to do this in some homework. But at the moment, I'm asking you your purely physical intuition. How these two guys move? Would it be, yeah, go ahead.
I was going to say if it's like electrodynamics with two current wires.
Yeah, there is something to it, yes. Would it be just electric charges? Then, of course, opposite charges would attract, same charges would repel. But here it's indeed I understand you are saying it's more like magnetic interaction, and that's correct. But you can use this intuition. It's a bit more complicated than necessary because you have you have in mind three-dimensional case. But it's certainly the direction of your thought is fine. It's the right way to think about the problem. Still, here you can predict the motion even without any analogies, just by the just try to you have to look at what kind of motion is induced, say, here by this vortex. Yes?
I was thinking about in between them.
In between? Yeah, you can.
Line in this one and that one would have some kind
Yeah, so what would you suggest is the answer?
of, I was saying at the points, at the center points, you're going to have sort of an area where it flips from a streamline going that way to a streamline.
Yeah. Right. It's slightly easier to look at just what this guy does to this guy, and vice versa. So what it does, it tends to move it like that, and this guy tends to move it like that. As a result, we will see it from the equation also, when you have opposite charges, they move with constant velocity. They have to move with the velocity, and the velocity is actually very easy to calculate. What do you think is the statement about this case 2, opposite vorticities, and they actually will move, and how you will find the velocity of their motion.
Adding the components.
You see the velocity induced by this guy, if this is the distance r, velocity induced here will be kappa divided by 2 pi 1 over r. And that's the velocity and the same with this guy. So they simply move together. It already creates some puzzle because it seems, well, it contradicts Galilean symmetry. Galilean symmetry would say that if things move with some velocity, they can, in a different frame, they would move with a different velocity. Here we have a fixed velocity. So there is some point to think of. Before we come to this point, let's have the answer in the equal case. What would you expect here?
So the initial velocity is both in opposite directions.
Yes, and so what do you think will happen to them?
So they orbit each other?
Yeah, they will rotate around each other. Actually, I can tell you in the end of the 19th century, there was such great scientists like Kelvin and some others were very much fascinated by the idea that atoms are made of vortices. It was they constructed quite remarkable schemes. Although they dealt with three-dimensional vorticity when vorticity form knots. We will see it later. But in any case, we have this thing, and it's clearly non-trivial, as we see from here. And we can write it down also well, we can write it down as epsilon alpha beta. Now the last point for today is that when I write it in this way, it becomes obvious that what can you say about this equation, this dynamical system, when I write it this way? I intentionally wrote it in a suggestive way. What general class of dynamical system it belongs to? Is it a Hamiltonian system or not? That's the question. Okay, we will leave this question for the next time. Let's stop now.